Hi everyone, we are continuing with our introduction to vector operations and the projective plane. The last video we covered the dot product, so next up is the determinant and how it relates to the dot product.
Okay, so that's what we end up with. That's what we get for multiplying the components, the like components together and adding them up. So the next obvious question is, well, what if we multiply the differing components together? So if we have two vectors, so this one has these two components, this one has these two components. What if instead of multiplying the two x's together and then adding that to the two y's together, that's the dot product, what if instead we multiply the x times the other components of the other one, and then the x of the second one times the other components of the first one? What do we get then? That's the determinant. The way to think of that is, so the dot product, so that's the next thing we're going to do. So the determinant. So the dot product, again, was basically straightforward one-dimensional multiplication in multiple dimensions. So you multiply this by this, you just scale this one by that amount, and you go out that direction. The determinant then is, what do you do? What happens when you multiply two numbers in sort of opposite directions in some way? In other words, if we have a box here, we end up with an area of 12, right? 3 times 4. That in some way, in some sense, is what the determinant does. You're multiplying the components in opposite directions, how they affect each other in the opposite direction instead of in the same direction. So, but again, we're not talking about perpendicular vectors here. We can talk, the vectors can be in any direction. So this would be, if they were perpendicular, then it would just be the magnitude of one times the magnitude of another. And again, remember, the determinant also gives you a scalar. It does not give you a vector. It's just giving you the number that's the magnitudes multiplied by each other. But what if the two vectors are not parallel, or are not perpendicular? Then you're going to basically make an area that is a parallelogram but it's not a right angle parallelogram. It could be skewed, but still multiplying the vectors, the components in this direction by the components in the other directions will still give you the area of the parallelogram, or in multiple dimensions, the parallelepiped. So the question is, if we're just dealing with straightforward numbers like 3 times 4, then everything's orthogonal and the area is 12. But if we're dealing with vectors, they might not be orthogonal. They might be at some other angle to each other, in which case we have to take that into account. That's what the determinant does. So first of all, just to check that what we're talking about is right, if this angle is 90, we would end up with just a rectangle, and indeed, the area would just be a times b, right? If, on the other hand, a and b were parallel, if this was b and this was a, then the area between them is 0. And that's exactly what the determinant gives us. So the way to find the area of a parallelogram you might remember this from when you were very little, is it's the same as a rectangle. The area of a parallelogram is base, the base, in this case a, times the height. Okay? Just multiplying. So the question is, in a parallelogram, how do we find the height? Remember I told you that cosine was adjacent over hypotenuse. Sine, of course, is opposite over hypotenuse. That's exactly what we have here. We have A, H, B. This is the height. This is the perpendicular up to this corner. So the sine of this triangle, the sine of this angle is the height, this leg, over the base. So the sine of theta in this picture is h over b. If you multiply the b by both sides, you end up with b sine theta equals h. So given that, if we know that the area of this parallelogram is base times height, just plug in the information that we have. So the base, in this case, is the length of A, and the height is the length of B times the sine of the angle between them. So this is how you find the area of a parallelogram. Now, the interesting thing is, so first let me, if you remember when you learned the determinant, let me take a step back here. The determinant of those two vectors, A and B, is AD minus BC. So if A equals A comma B, B equals C comma D, the determinant is we take A times D minus B times C, and that gives us the determinant. So what I want to show you is that this gives you the area of the parallelogram. So how can I show you that? We have a parallelogram A, B, the vector or the angle here. Now, we need this distance here. The vector perpendicular to this one would go up here, right? So this is perpendicular. And then we would have sort of a complementary angle. And then the height would be here, right? So if the distance of this is A, and then we make the distance of this also A, this is just the perpendicular vector. Then we take this angle, project this onto here, and we get H. So how do you take the perpendicular of a vector? If the vector is A comma B, you just reverse them and make one of them minus, okay? So this is the perpendicular of this. The length is the same, you can tell, because the components are the same, but you go back. So I can show you if we have 2 comma 1, instead we go back 1 and up 2, then those are obviously going to be perpendicular, okay? So what we're looking for is we want the area equals the base times the height. So if we take the perpendicular vector here, and we take this angle, and this is B. Again, what's the cosine of that angle? Is the adjacent, which is this, over the length of the hypotenuse. Okay, so we're looking at this. This is a right triangle too. And instead of the sine of this one, we're looking at this angle. The cosine of this angle is equal to the adjacent leg over the hypotenuse. So it's h over b. And if you can see that these are all square, so this is the h that we want, but the same h is here. So then h equals b times cosine of that complementary angle. Okay, so what's the area of the parallelogram? It is the length of A times the height. And what's the height? So it's the length of A times the length of B times cosine of that. Does that look familiar? Yes, that is the dot product. That's the dot product of A perpendicular and B. Because the length of this is the same, it's in a different direction, so we can cosine it. So if we take, so we have our two, the two vectors are A equals A comma B, B equals C comma D. Now we're going to take the dot product of the perpendicular one times dot product with B. So we get that A perpendicular dot B equals, oh here, so A perpendicular equals negative B comma A. So it's negative B comma, or I'm sorry, negative B times C plus A times D equals, rearrange that, AD minus BC. So there you go. This is how we define the determinant. And indeed, it will give you the area of the parallelogram. And then that's in 2 dimensions, but the determinant actually works in multiple dimensions. So if you had a 3-dimensional parallelepiped that went, say, up like this, like that, and then here's A, B, and then this is C, then to find the area or the volume of this, you take the area of the base times the volume is the area of the base times the height, once again. So what's the height? The height is if you dropped down from the top corner of C down to here, that's the down to the base, that's the height. So the area, once again, is the area or the volume is the area of the base times the height of the parallelepiped.
Okay, that is it for the determinant. Next up, we're going to start looking at the cross product and how it relates to the determinant. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.